Next up, we have Åsa Widen from the Swedish University of Agricultural Sciences, and she is going to be talking about climate change.
Good morning, everybody. My name is Åsa Widen. I'm from Sweden, and I work at SLU up in the north of Sweden. I will talk about climate change in the context of environmental flows and change hydrology in 3 river basins in Sweden. We always work in collaboration when we work with the ecosystem management, because we really work with ecosystem management. And we just point out that collaboration with hydropower companies, authorities, NGOs, and local stakeholders is really important. The background to our motivation, our work, is the status of world river system, but also its climate crisis and energy crisis, where hydropower plays a key role into the conversion into a renewable electricity system, and that's really important for us. Meanwhile, we understand that river ecosystem are really affected by hydropower, which is one cause of diversity crisis. We will have an increased pressure on the rivers ecosystems due to climate change, and that calls for environmental assessment. We need to understand what is coming, and we need to understand how we can what possibilities we have to improve the status of our river system. Meanwhile, we are supporting the energy production and climate crisis. So that's a $1 million question. We need to find some win-win solutions. Anyway, we need to find some suggestions of solutions with consideration of climate change and river ecology. In the rivers in Sweden, we have a great loss of different kinds of habitats. We have, as you see here in the Ume River, we have a great loss of lutic habitat. We have a great loss of riparian habitat. And when we are working with ecosystems assessments, we are mapping what's lost to be able to understand how to construct possible mitigation measures for the future. We are working a lot with hydropeaking, and our definition is fast changes of flow, water levels, and starts and stops or zero flow, and their interactions. And why is that important? Because when you have start and stop or zero flow, water levels and flow will divert. So, as you see up here, we have a green line for water levels going down when flows goes up. And that's really unnatural for an organism in a river, because they are used to, when the flows increase, water velocity increases, and so should the water levels do as well. And this is a quite common situation in Sweden, due to that we have utilized all fall heights. We have mapped all fall heights in most of the large river catchments in Sweden, from the south to the north, to understand how much lutic habitat is remaining. And we have recently got most of the results, and we realized most of it is lost. So what's happened with the dam without fall height? It will act as a bathtub with a completely flat surface. So when you are removing the bottom plug, the level in the bathtub will decrease, and water levels and water velocity as well. So the river will act like a gigantic bathtub, which is kind of unnatural for a river. We've been looking at the Ume River, the Ljungan River, the Lagan River, and done ecosystems assessment in all three catchments in collaboration with Statkraft, but also many other large hydropower companies in Sweden. I think actually we worked with most of them. We have worked with a climate scenario A1B, which is a quite moderate scenario, if you can use that word. We are using 83 historical years, weekly data, environmental effects. We are using hourly data and high resolution. So we are switching scale, timely and geographically, back and forth and so on. And then we are studying different kinds of effects. So to be able to do this properly, we have to map morphology restoration, we are mapping connectivity, and we are suggesting flow restoration, which ends up in combination of different kinds of measures in scenarios. For the Ume River, it ended up in 30 flow scenario. Lagan River, we had about 15, and Lagan about 15. So we describe energy consequences on the energy system, and we try to project the environmental benefits. Today, we are not going to talk about 50 different kinds of scenarios, because then we need a week or so. So we will stay at minimal flows or a base flow where we forbid start and stop and zero flow. But we are combining these scenarios with other functions like connectivity, spring flood, altered water levels, and et cetera, and morphological measures. When we are modeling forbidden flow, the water are always released through the turbines. And that's because we want to maintain the energy production. When it's not possible, we are thinking you might be able to use this water for bypasses, connectivities, or because that's spill water, and it's really important that we take good care of it. We are deciding the amount of water based on the technique. And it's often mean annual low flow. Sometimes we can have a really large Francis turbine, and for that reason it's not possible to use mean annual low flow, and in these cases we will spill the water. So some results. We will have an increase in hydrology, not very surprising because everyone knows it will rain more in the future. And it's really obvious that will also increase the electricity production. More water, more electricity, quite simple. We have also mapped for all these three catchment area, the amount of hours with standing water in these base tubs. And it depends on the location. In the reservoir, you have a higher degree of standing water. We have one example from Lagan, which was about 6,500 hours during a year. So almost a whole year. This is incredible. But normally we have like 2,000, 4,000, something in the between. And you can have some station, you have 2 start and stop every day. And so this is interesting because what will happen if we forbid it and say, if there are any possibilities with forbidding zero flows and standing water in a river? Yes, we looked up using our mapping how much habitat, as in hectares, would be improved by a higher water velocity, which also means higher oxygen levels during summers, and so on and so on. And it was quite a large amount of hectare. But this is after we have made all our morphological measures. So you have to combine e-flows with other kinds of measures. And you have to combine the morphological measures with e-flows. Otherwise, it can be so that it won't work due to standing water. Another example, this is from Storuman Reservoir, and we are looking into the future. So for a dry year, we can have 8 weeks of standing water in Storuman. But in the future, for the same year, we can have 12 weeks. It's a large river with the tap closed during 12 weeks. So with e-flows, like scenario 9, where we have forbidden zero flows, we have water to bypass channels, we have water to fishways, can we manage that when we study the reservoir filling degree? Do we have enough water? So the difference, it's not really large. So maybe it's possible. When we look at the losses, what happens when we forbid zero flow? We were really surprised because it was 0.5% of the production in the Ume River using 83 historical years. But in Ljungan and the Lagan River, the production increased. It was really remarkable. But it's because if you think of efficiency curves, and you go from 400 cubic meter down to 0, you have some parts of the efficiency curves which is really bad. So because of that, you will gain energy, electricity during nighttime with forbidden flows. So we are changing the electricity pattern. And maybe we will produce energy when the society doesn't want it. And this was also something that we looked at for all hydropower stations and for the whole catchment. And in total, if you look at prisavsnitt, Yeah, I was really surprised by, it's alive. So we will lose, in average, for this station, this is Ljungan River, about 9%. And that means that we are losing some capacity according to regulation and to have when we are forbidding zero flow. But we will gain electricity during night, and we will increase their production during summer. And in the context of climate change, these losses will decrease. So environmental flow measures like forbidden zero flow will, the effects will decrease in the future. And you can also see that we will have a change over the year. So during May and June, July, when the ecosystem really needs measures, the effects are really small. So maybe we can be a little bit flexible to have the rules during summertime and so. And this is an example how you may find solutions. I don't say this is how to do it, but I say this is a suggestion. Don't just complain. Innovate, try to find solutions, discuss, and so on. And maybe we need to do all this in the context of climate change, because the pressure on the riverine ecosystem will be higher. So we need to move further. We need to test measures. Maybe we have to change other consumption patterns and so on. So, thank you.